New text, new draft text. Control, an introduction. So please go and make sure that, let's see, I'll give you guys till Wednesday to have those printed. You only need the first 6 chapters. Let me just double check that. I'm pretty sure that is correct. The first 6 chapters are required for this course. If you do go on to do Control 1 as an elective or as a grad course in the fall, then you will, or not, yeah, in the fall it's being offered. Then you will use the rest of this text too. But for now, you only need through chapter 6. Oh, goodness. Control.pdf. Yeah. Okay. Through chapter 6. I was right. Good. So, this is the title page, but now it's spring 2019. I had to update the date. Okay, so we're on the first chapter, and this is a big transition in this course because it's going from system dynamics to control. And so this course is called System Dynamics and Control. And so we're learning system dynamics, which we've essentially concluded with the last lecture and the exam. And now we're going to be using system dynamics to learn how to do system control. And this topic is vast, but you only have, as required in our curriculum, 5 weeks of this control topic. And I would say that control underlies like a huge amount of modern technology is based on the idea of control, and without control you would not have anywhere near the level of technological advancement that we have. So it's a very important concept, and I think that you guys are going to get a pretty good taste for it in the last 5 weeks of this course. We're going to learn how to use it. We're going to learn kind of like what the concept is, what the idea is, and then we're going to learn how to apply it and to do design with it. But there's a whole lot there, and we're only going to get to the very beginning. Although it'll give you enough to, like, you could throw together a controller though. Like that's like we'll get to that level. Do a little bit of controller design, but there's a lot of stuff that would go into that. So you can explore it further if you look at the elective courses like Control 1, Control 2, Linear Systems Theory, Robotics, the Machine Intelligence course that I'm offering. So like there are like Embedded Computing is for mechanical control, that one as well. So there's these courses that I teach, and some of the ones that Chandwan teaches, at least, and there might be some others, that go more deeply into control. And I would recommend that you check those out. I think they're pretty awesome. So let's get an introduction first. So control theory is the study of control systems, which are systems that control the behavior of other systems. Okay? Pretty basic definition. We want to study a system that is there to control another system. Like how do we do this? How do we analyze these control systems? How do we design them? This means that control theory is fundamentally about design as opposed to the analysis of many engineering topics, including system dynamics. So system dynamics was about analysis, right? You're learning how to mathematically model these different systems and predict what will happen. So we're analyzing them and maybe characterizing their different characteristics, defining their characteristics, or characterizing them. So they are. So system dynamics is very much an analytic tool. It can be used for design. I mean, most of your engineering courses are pretty analytical, and there's not a ton of time talked about design. Although I would say that our faculty and our curriculum are more design-oriented than many. But design is kind of like the goal of a lot of engineering. Like you want to get to the point where you can actually design something new, right? Not just analyze something that exists. Or for instance, putting like a bounds on the specifications of what you're doing. Like you want to design something new. You want to say, oh, okay, this is what the performance is now. How could I make that performance better? Okay, so design is what control theory is really oriented toward. And there is quite a bit of analysis as part of it, but a lot of that's system dynamics analysis. And there are some new analytic techniques that get introduced in control theory, but they're all oriented towards how do we make the system perform the way that we want, which is inherently a design question. So, good. In control theory, a system, which is usually in control theory called the plant. Okay, this is just like a historical naming convention. It's called the plant. Whoa, really thick pen. Is analyzed often with system dynamics. Then a control system is designed to control the plant. So you gotta check out the system that you're trying to control. So the plant needs to be analyzed, and then you want to design a control system to go alongside that plant to control what that plant's going to do. Okay, and that's very broadly what control theory is about. It's like, how do you design this system, this controller system that's going to control the other system? So a control system usually controls the plant by changing one or more of the plant's inputs. So you can think of the plant as being this box, say. Oh my. I know. Not even pressure sensitive crayon. Let's just say it was a single input, single output system, but in general there could be multiple inputs and multiple outputs. If this is your plant, the controller is going to mostly influence what that plant does by controlling its inputs. Okay, controlling inputs to the plant. The plant's outputs, so those are in, out, the plant's outputs are going to be things that we want to know about what's going on in the plant, and or things that we want to control that are going on in the plant. So we want, for instance, if our plant was the system that is maybe a motor connected to a maybe it's comprising like a single joint of a robot arm, say. So the angle that joint is at would be maybe the output that we're interested in. We would like that angle to be, say, 32 degrees at some point, and that would be the output that we're interested in, is what is the angle of this arm. Other outputs could be like the temperature in the room, or maybe the altitude of a plane, or something like that. So there's like all kinds of different outputs that we're interested in, and that we would like to have behave in a certain way. Okay? The inputs are things that are going to change what's going on in the plant, hopefully to change what the output is going to be. Now, if a plant is mathematically modeled with sufficient accuracy, a controller can specify the plant's input, which is the controller output, to produce the desired output. So you could think of, I'll move this up here a little bit so you can see it. Sorry. So the input to the plant is actually the output of the controller. This is one arrangement. This is not the only arrangement, but this is one. So this would be the controller. And the controller, it knows what you want. So this would be the command. It would be the command of what we want the controller knows. And if it knows the plant super well, has a great idea of what's going to go on in the plant, it can just simply say, oh, okay, then if I want this angle to be at 45 degrees or 32 degrees or whatever we said, then I'm going to need to put in this amount of voltage to make that result happen, okay? That would be, like, its input to the plant would be the voltage that it puts out. So that would be one way to go about controlling what the plant does, okay? This is called open loop control. However, most plant models are not understood well enough to do this. It is especially difficult to model outside disturbances like sudden jolts from being bumped and environmental interference. So if you say, oh, I know this plant perfectly well, I need to have this much voltage to get this arm to be in a certain position, you're relying on your model being perfect and nothing that you didn't predict ever happening, right? So you're very reliant on a lot of things that are probably not completely true. So for this reason, most control systems include feedback, which is to say measurements of the plant's outputs. So feedback would be taking this output and feeding it back and doing something with it back here, okay? So we'll modify this a little bit later, but this is feedback. So the idea is, okay, now I'm feeding back the output, what it actually is. So now the angle of the arm is being measured. And you say, oh, I want it to be 32 degrees. Well, it's actually 34 degrees. So now your controller has to decide what to do with that difference, okay? And in fact, oftentimes what we do is we simply subtract. So we move the command back here, and we say, okay, what's the difference? Summing junction here. So I take the difference between the command and what it actually is, and then I say, okay, now the controller gets to decide what to do based on that difference. Not based on what I want, based on the difference between what I want and what actually is going on, or at least my measured value. I mean, assuming that I can measure it perfectly is quite an assumption, but at least I can have an idea of what it is. So that is approximately the feedback control scheme that is ubiquitous. It's used most control systems. There are some open loop control systems though. Like, I'm pretty sure that speed indicators on like small appliances and stuff are just, they're not being, there's no feedback on them. There's no measurement of like how many RPMs my blender is actually going at. Maybe it's supposed to be 8,000 RPM at this setting, and like it's probably off by 20%, but nobody cares, right? Doesn't matter. So there's no feedback on it because that application doesn't require it to be precise. But when it's a system that you need to be pretty precise, and you want, so like the difference between 8,000 and 7,000 RPM might not be that significant in your application. But in some applications, it would be very significant, and you would need to have feedback in order to do the control. If a plant is mathematically modeled with sufficient accuracy, oh, that was the old stuff. Like, that sounds familiar. For this reason, we feed back the measurement of the plant's outputs. These measurements are fed back to the controller, which determines its output, or the plant's input, from this information. Determining how the controller should respond to the feedback to control the plant's output is the subject of much of control theory. So then that's the question is like, oh, okay, what should I put in this controller? Like based on the fact that I've got this command and I've got this feedback that are, usually different values. What should I do? How much voltage should I put out if that's my output of the controller and input to the plant? Or like if I've got multiple inputs to the plant, like which of them should I be engaging and how much in each of them should I be engaging? And that's what the controller has to decide. So that's the topic of a lot of control theory, is what to do with this difference and what to do with this controller, what to put in there.
Would it be real, like if you put the cruise control on?
That is a good example of a control system. So when you put cruise control on, you're setting the command to be, say, 67 miles per hour. It's like a cool, it's like a good spot right there. 67, 68. Sometimes when I'm feeling real dangerous, 69. It's getting close though, and I get worried, especially going through Nisqually. But yeah, say you set it on that, say 67, and you start to go up a hill, and then your car starts to slow down, and the actual speed drops to like 63. Then there's this difference to make up, and so the car's controller has an input to the system, which is like how much to essentially press the accelerator, right? How much what the speed of the engine should be, and the gearing that you're in, and all that. So you have this input and to the system, and you have to decide how much should I do. It's like if every time you were below the speed you want to be at, it just went full throttle, and every time you were above, it like braked for you, that would make for a wild ride, right? And it would be very inefficient. So deciding what to do, I mean, like, besides like full acceleration and like braking when you like, besides those extreme options, what you should do at any given moment of time is like how you designing a controller is doing that essentially. Yeah. So cruise control is a good example of a feedback control system. A thermostat is an example of a feedback control system. Turns on your furnace, turns off your furnace. Yeah. There are a lot of examples of control systems. Actually, a purely mechanical control system that's pretty fun is the toilet. The float valve on a toilet, it's essentially measuring the height of the water in the tank. When it gets to a certain height, it shuts off it closes the valve to supplying water to the tank. And then when you flush it, it gets lower, it opens up the valve, and it starts refilling. And then, yeah. So it's an example of one of the earliest control systems that we know of that were designed. Is like a float valve shut off. People made water clocks. Those are some of the first controllers that were ever control systems that were ever designed. They created systems where you could have a constant flow of water, a constant speed flow of water, so you could keep time with the flow of water, how much water had come through. So pretty cool early systems. But yeah, control systems have been around actually since, I mean, those were practically ancient examples, thousands of years ago. I think the Greeks did a few, and then it took a long time. Steam then was the next like big step in control technology, and then electronics coming along really was the next big leap in control technology. So, but like a lot of the theory that we'll learn is like 50, 60 years old. Some of the newest theory that you'll learn in engineering is actually control system stuff. Computers is the newest, but yeah. And in a lot of ways, computers are possible because of controls that preceded it. So, yeah. So, not to say that it's anywhere near being like a field that has it all figured out. There's a whole lot of stuff. Control systems are still being designed, and new methods of control are being developed. There's an AI sort of take on doing control systems, which you're not going to go into in this class, but we will talk about in machine intelligence if you take that course. and that's pretty cool too. So that's like very new stuff. So, great, and this is all very useful. So if, good. There are several types of controllers used in control theory and many adjustable parameters for each type. So what we'll talk about is we're going to go with a certain class of controllers, which are of the PID class, okay? And I don't know, I've heard different estimates, but the number of controllers out in the real world that are PID, it's like the percentage is like 90+% of the controllers out in the world are of the PID type. And so that's the type that we're going to focus on in this course for obvious reasons, because it's the most common. It's very intuitive, and you're most likely to encounter them, and they're very robust. Like they'll work in a lot of different situations, and they're good enough in most applications that require control. So that's why we're going to focus on that. But there are a lot of other types of control, very advanced types that are required for more advanced systems. And one of the things in PID control, so PID control usually comes with 3 parameters that can be adjusted. So 3 gains, we'll call them. And even when you go down to the most simple, just the proportional controller, the P controller, you have 1 gain. But you can adjust those to, if you're using analog equipment, then infinite number of real number values, the gains, right? So the gain could be like 52, but it could also be 52.00001, right? It could be, there's an infinite number of possible values for these gains, and so you have a really large design space. Even if you just choose a PID class controller, type controller, you still have an infinite design space where you can choose 3 variables out of all the real numbers. Assuming you have that much ability in your actual physical controller, which usually there's some digitization, so you don't have that much, but you have a lot of options. Huge design space. So which type of controller? So PID is the one we're going to focus on in this class, but proportional integral derivative, we're going to talk a lot about it, so yeah. But so like PID control is one type, but another type might be best in a given situation. And determining these parameter values, like the gain values, are some of the primary tasks for the control engineer. There are design trade-offs to be made. Some controllers will be more expensive to implement than others because they will require more expensive hardware. So that's one example. Some controllers will perform better than others in some aspects we will now explore. So we're going to talk about performance in the first lecture in this. This is just the intro sort of page. But whenever you design anything in engineering, you have a lot of different considerations, a lot of different variables, you could say. You could represent it as being variables you're trying to optimize, right? And we're going to talk about some of them in the next lecture. And anytime you do design, you should think of it as being a sort of like an optimization method with this really large design space, okay? Usually it's like infinitely large. You could choose from an infinite number of possible choices of controller or whatever it is you're designing. And there are two significant dangers here. The first danger is the one that's the most common, is an artificial narrowing of your design space. So you see this happen a lot when somebody has an early idea, like a brainstorm idea of, oh, we could do this. We could use this sort of like approach or this geometry or this method. And that is sometimes a good choice to go down that route, but you oftentimes will artificially narrow our design space because it causes us anxiety that it's infinitely large, okay? And we want to just focus in on something and like make that one work. And the other danger is to never narrow it, to keep it too open. Sometimes you need to narrow it down and say, okay, I have good reason to believe that this class of controller is going to be best for this application. you should always make like soft design decisions, but when you make that design decision, you really do need to commit to it for a little while to see if see what happens when you go that direction. So you can't constantly go back and second guess the old design choice and never make progress. But you also you shouldn't narrow artificially. A lot of people narrow themselves down into a space that it becomes intractable, or it becomes something that they can't actually achieve, and then it's because they made a decision like 50 decisions ago that was artificially narrow. So, and sometimes it's hard to go back. So keeping that flexibility is good, not falling prey to that. So now that we're talking about design and control systems, we want to be careful that we don't artificially restrict our design space. Okay, so that's a big thing to always worry about. Good. And if you want to learn, we'll talk about design in this class quite a bit going forward, but if you want to learn more about design beyond this class, I'll mention that Dr. Washko teaches some classes specifically on design and creative problem solving that I hear really good things about. I should sit in on them sometime. I think it'd be fun. So yeah. Maybe one day I'll find room in my schedule to teach one of those too.